Okay. Got it. Okay, but not. So does it record automatically? Do we need to record separately? No. Okay. Okay. Hello, everyone. Welcome again to P&S DRAM Bonder course. This course is, as I said in a minute later, earlier, this course, this session in particular is a joint session with P&S Remulator. So if you came for exploring emerging memory technologies, it's also the correct place. So first I will go over a slide deck. And after I'm done, another Hassan will go over another slide deck for the remulator part. So this part is in particular for DRAM Bonder and FPGA-based exploration of DRAM and RowHammer. And this is my name. I am Giray. I am a PhD student in Safari Research Group under supervision of Onur Mutlu. Okay. So here is the content of basically this this course. Okay, in this course, we expect you to learn how modern DDR4 DRAM operates in detail, how to characterize the DRAM chip's behavior using an FPGA-based infrastructure, and how to use DRAM Bonder. DRAM Bonder is the name of the infrastructure to develop your own DRAM experiments and gain hands-on experience in studying these DRAM characteristics. We expect to reach to some key takeaways. So this P&S is aimed at improving your knowledge in computer architecture and memory systems with a focus on the memory systems, and your technical skills in running DRAM experiments using real devices, and your critical thinking and analysis abilities, and your familiarity with the key research directions in memory systems and DRAM characterization. We also hope to or aim to improve your technical presentation skills for this project and in general as well. And we also expect some good communication skills at the end of this course regarding this research topics. Okay, so the key goal of this course is to study real DRAM chips using an FPGA-based infrastructure to gain new insights into DRAM behavior. So DRAM is short for dynamic random access memory, and this is the prevalent technology used in the main memories in your computers, mobile devices, everywhere. Okay. So this course has some prerequisites. If you end up deciding that you don't have these prerequisites, maybe you need to reconsider taking this course. The first one is So this digital design and computer architecture is a course that probably all of you took in your first year or second year. And an equivalent course is also satisfying this concern. So especially we want you to start with a well understanding of the topics like combinational and sequential logic, hardware description languages, the von Neumann model and instruction set architectures, assembly programming, microarchitecture, meaning the CPU core architecture, for example, and the memory hierarchy. And so you can consider like main memories, caching mechanisms, these kind of architectural components in this category. So we expect you to have a good understanding of all of these concepts. And we also need you to be familiar with FPGA programming. In particular, we use Verilog HDL in building this DRAM Bonder infrastructure and some Xilinx tools. And depending on your project, these might not be a must actually, but it's always good to have these familiarity to these things. And I think the second bullet point here is more relevant. It's so you need to be comfortable with coding and programming. We usually use C++ and Python for running experiments and conducting simulations for the emulator part as well. So it's always important in this course to be comfortable with these languages. If you're more comfortable with other languages, partially you can also do that. Like if you don't want to do Python scripting, you can use another scripting language, of course. But if you will run DRAM Bender tests, then you will need to have some familiarity with C++ programming language because the API is written in C++. So we also want you to be excited about low-level hacking and also memory reliability, security, energy efficiency, performance kind of topics. And also some interest in discovering why things do or do not work, and solving problems, making things work, and getting your hands dirty to do that. Okay, so wait. Hasan, what did you?
Yes.
You sent something on the chat. What is that?
So like you mentioned like an equivalent course. So just put that equivalent course there. Yeah.
Okay. So you can check the chat and see the equivalent course. I think it is computer engineering. Okay. So this course is offered by Professor Onur Mutlu. Am I muted? Am I not? Okay. And Onur Mutlu is a full professor in ETH Zürich, both in electrical engineering and computer science departments since 2015. And he's a Strecker professor in Carnegie Mellon University in the US, both in electrical and computer engineering and computer science departments. And he holds a PhD from the University of Texas, Austin. He has work experience in like multiple top tech companies like Google, VMware, Microsoft Research, Intel, AMD. I think this list is longer than what you see in this slide. So Onur Mutlu is the leader of Safari Research Group, and we are all his students. Our team consists of some PhD students, master students, and some visitors as well. Okay. Okay, yeah, you can see more information about Professor Mutlu in his personal webpage, and you can reach him through this email address. And you can also see the project's website, in particular in his website, for his interested research topics and what projects he offers. So he conducts research and he teaches in computer architecture, computer systems, cybersecurity, and bioinformatics in general. And you can make the list longer, of course, with finer granularity. For example, memory and storage systems is very relevant to what we are focusing on in this course. So here is the team of the supervisors for this project. I'm Giray. Next to me, you see Ataberk Olgun. He was the lead supervisor last semester, so you can also bug him whenever you have problems. And we have a very strong team of TAs, as you see the names in order with the pictures here. And you can see all the group members of Safari in this particular link here. By the way, I uploaded all the slides to our course webpage, so you can download and click on the links easily. We have a newsletter. Another one is coming up actually, but the last one is from December 2021. This is a photo of our group. There are more members than us. We are more than 38 researchers in this group. And this is our group motto, Think Big, Aim High. Our research focus areas are concentrated around computer architecture, hardware, software, code design, and bioinformatics. And here you see again memory and storage, in particular DRAM, flash, and emerging memories, interconnects, heterogeneous parallel systems, so on. So we basically focus on pretty much every single part of computing systems environment. Like we look at the microarchitecture, we look at the main memory, we look at the storage systems, all the networks between them. And we also go in higher level in the stack. We look at hardware, software, code design, and bioinformatics applications. Okay, so we have some course requirements and expectations from you for this course. We expect you to attend our meetings, and we expect you to have one-to-one meetings with your assigned supervisors to make progress in your research. These meetings are important not only for reporting your progress, also for solving your problems. If you feel like you're stuck, don't waste time and immediately send a message to your supervisor. And we also expect you to study the learning materials. We will provide you with some papers, and we will also have some paper presentations throughout the semester. So those things can help you with improving your knowledge and solving your problems for a project as well, or having a better vision of your project. Okay, so yeah, so we expect each student to carry out a hands-on project. So we don't work with groups. So each student has a project, and we will discuss the potential projects next week. But you can also check the slides from last year and see what kind of project we offered in the last year. Okay, so participation is really important, as I said earlier. So please ask questions, contribute thoughts and ideas. Don't hesitate to brainstorm. There's no silly idea. And please ask for help when you're stuck, and keep reading the relevant papers. So we are here to help in your projects. And if your work is good, we can, beyond the semester, we can keep working on that. And we can make it published in a top venue, basically. And it is really important for your own career as well. Okay, so this is the course website. You can reach from this link, and we have very useful information about the course over there. I already sent you an email about the materials that I will show in the next slide. And please check your email frequently for announcements. Because yeah, email is the main communication channel between us. So these are the required materials and recommended materials for this first week. It's a bit heavy in the initial weeks because you need to have some background information about all this environment, but it will be better in the following weeks. So we already have a DRAM Bender tutorial about how to use DRAM Bender. It's a recorded video from last semester. You can access it from this YouTube link, and it's already on the course webpage as well as week 0's meeting. And we have also SoftMC lecture, and we have papers published explaining all these infrastructures. So SoftMC is the older version of DRAM Bender, basically. It was published in 2017, and we improved it significantly. Ataberk is the main person who actually improved it and made it a new, more useful infrastructure with its own instruction set architecture. It's very flexible and easy to use tool to test DRAM chips, and it's called DRAM Bender, and you can see DRAM Bender's paper as well on archive. And you can also see a bunch of examples, example projects using DRAM Bender and SoftMC to do basically cutting-edge research, and those works are published in top venues like IEEE Security and Privacy, Micro, HPCA, ISCA kind of conferences. Here's the tentative weekly schedule. This might change a lot throughout the semester. So In the week 0, as I said in a minute ago, we have a YouTube recording for this. Please check this video. You can understand. So throughout the semester as well, please refer back to this video whenever you have problems with using the DRAM bundler. It's a good tutorial that goes step by step how to use the tool. And this is today's meeting. We will talk about the logistics. We already talked about logistics, and we will have a quick introduction to DRAM. We will not have an introduction to SoftMC this week. Probably we will have it next week. And next week, we will also talk about the available projects. And in the following weeks, we will present you different papers that use DRAM bundler to conduct their experiments. So these are focusing on different parts of the system. For example, there are papers focusing on this RowHammer problem that you might have heard about. And there are papers focusing on generating random numbers using DRAM or overlapping some latencies in DRAM maintenance operations and dynamic accesses, for example. All of these papers you see here are using either DRAM bundler or a version of SoftMC or something relevant. I hope these will be good examples for you. Yeah, every week we will have you will have one-to-one meetings with your assigned supervisors, and every 4 weeks roughly, it can be more frequently or less frequently, we will have a group meeting for project updates. Okay, so for meeting 2, we will announce the projects, but this is still TBD, and probably we will have some introduction to SoftMC, an older version of DRAM bundler, and we will present that paper to you. Okay, so the supervisors would like to help you with selecting a project and matching your interests, skills, and background. So please let us know, earlier is the better, about your interests and about what kind of projects you're interested in and your skills and background. And we can also discuss before you choose a project. So it's not like you choose a project and you're stuck with it. You can choose a project, you can ask questions about that, you can come to our office and talk about the details. You can choose to move to another project after that. So if things are not clear for you, probably a lot of details will not be clear to you when you see the project definitions, because we keep them a bit open-ended so that you can explore and you will have freedom in your research. But you might not be aware of the challenges on the way, and we're here to help you both in choosing your project and executing your project. And you also have an option to look at the remulator projects as well, other than DRAM bundler projects, and we are also flexible about that. You can choose other projects as well from remulator part. But it's really important that you study learning materials for our next meeting. So please go over the required content, at least. Okay, for the performance assessment, we expect you to learn how DRAM operates and perform DRAM characterization using FPGAs for DRAM bundler part. And we expect you to achieve the goals of your project. Each project has a goal definition, basically. And you should deliver your code and results with sufficient documentation. So we might ask you to write a report. It is very likely, but not a must. We are also okay with some well-documented source code and some presentation. So you will prepare a final presentation and present your work to all members of Safari so that you can get a good feedback from a larger audience. And this is important this is a really important milestone, the final presentation. After this milestone, we can decide to continue working on this project and making it a real high impact research paper. Okay, so this is the end of the DRAM bundle part. I hope I didn't take too much time. So now, okay, this slide is wrong actually. Now, Hasan will take over and he will talk about the remulator part. And then we also want to hear back from you about your thoughts. I see your slides, but I cannot see your face.
So yes, sorry, I didn't realize my mic was muted. So hello everyone, welcome to this P&S Exploration of Emerging Memory Systems course, or we can just call it P&S Remulator, because we are mostly concerned with the DRAM and memory system simulator called Remulator. Yeah, in this first meeting, we will briefly cover the logistics course and a quick introduction to DRAM-based memory system. So in this course, you will learn in detail how modern memory systems operate. You're expected to implement or design new DRAM and/or memory controller mechanisms to improve system performance, energy consumption, and reliability. You will simulate and understand the behavior of the memory system under different workloads, such as machine learning, graph analytics, and genome analysis. So this P&S course is aimed at improving your knowledge in computer architecture with a focus on memory systems. You will gain technical skills in simulating modern memory systems. You will improve your critical thinking and analysis while you are designing, implementing, and analyzing your results. And finally, you get the chance to interact with a nice group of researchers in the direction of computer architecture and memory systems. And finally, we hope you can get an idea of what are the key research directions in this field. Yeah, and of course, you will improve your presentation skills through the final presentation. So the goal of this P&S course is to let you learn how state-of-the-art memory controllers operate, how to design new DRAM and memory controller mechanisms, and how to evaluate your designs using a high-level simulation. So there is some pretty strong prerequisites for this P&S Remulator course. So first, you should have a solid knowledge of computer architecture. You should know how modern computers are organized. You should also know about basically how the DRAM-based main memory works. So the two acceptable course for this prerequisite is the Digital Design and Computer Architecture, the DCA, and offered by the CS department, or the Computer Engineering course offered by ITED. So both are bachelor level courses. So yeah, we think they are like appropriate prerequisite courses. And second, because in this semester, you will be engaged with Remulator 2.0, a refreshed and rewritten version of Remulator that we have been developing internally. And because like you will be working with us on this like an early stage of a new simulator written in modern C++, we expect you to already be very familiar with how to develop a large C++ projects using modern language features and be familiar with the modern build system. So yeah, if you think like you are not very proficient in this aspect, we would recommend you to take a look at those DRAM Bender projects. So the C++ requirements there are not as strong as it is in the P&S Remulator course. So yeah, and you will get an idea of what the Remulator and P&S DRAM Bender projects look like in our next meeting. And of course, you should be motivated and interested in making systems more efficient and to solve problems. You should also be interested in understanding the software design, the software development workflow, and how to co-design software and hardware so that the whole system can be more efficient. So we have a tentative course schedule. So the first 3 weeks, we will cover the basics. So in this meeting, we are covering the logistics and a brief introduction to the course. In the second week, you will be introduced to a list of available projects defined by us. So I just want to mention that like you are not bounded to these projects. If you have your own ideas in memory systems, be it DRAM Bender or Remulator, you are more than welcome to write your own proposal and send them to us early. And yeah, if you think it's good, you can choose to do the projects you like. Or otherwise, if you don't have like a very concrete idea, you can try to learn the basics in this week and choose in the second week from the list of predefined projects proposed by us. So in the third week, we will undergo a tutorial to the new version of Remulator. Notice that you should have picked or proposed on your own a project by week 3. Otherwise, we will have to randomly assign you to projects. And afterwards, we will premiere the paper presentations that our group has published in the past. And meanwhile, you should have regular meetings with your supervisor about the progress of your project. And if you have any question, that's the best time to put forward and try to get it solved. And in week 9, we will try to have a milestone presentation where everyone gets to share their progress, and also everyone can have an idea of like what other people are doing. You should basically present what you have achieved and what are the remaining challenges. So it's like a checkpoint for your project. And this might also be tentative, but yeah, we try to schedule it at week 9. And from week 9 onwards, yeah, you should like just continue the project meetings with your supervisor, and we will decide on a final presentation date. So if you want to propose your own project, so like this applies to both Remulator and DRAM Bender. So if you have your own idea or you would like to do something on your interest, your proposal should basically have the following 3 components. First, you have to motivate your project. Basically says like, why do you want to do this? Do you have any insight from prior work, prior papers, or do you recognize like there's a problem to solve? And second, you should have a clear definition of your goal. So what do you want to achieve in the end for this project? You should be precise and be practical. And we would recommend you to split the goal into 2 parts. So first, you should have a primary goal, or in other words, like this is like the minimum requirement that you want to satisfy. And on top of it, you can try to define the secondary goals. which could be the extension of what you have based on the primary goal. And finally, you should also define your expected results. So these are basically the deliverables of the project, or in other words, like what do you want to show in the final presentation? So this is also important because, yeah, I think it will help you to plan the workload of the project well. And while you propose this to us, we can also give you feedback on, let's say, whether it's like practical in, let's say, this semester, or how you should like refine your project designs and goals. And the predefined list of projects will that are offered by us will also basically have the following structure. Yeah, so the course requirements and expectations, these are like almost the same as what we have just discussed in DRAM Bender. Basically, attend meetings as much as you can, study the materials, and get in touch with us whenever you have questions. And if your work is really good, you have the chance to publish it. So for the performance assessment, you should show that you learned the basic knowledge in this field. You should have achieved at least the primary goal of your project. And finally, you should be able to deliver all your code and results with reasonable documentation. And of course, your presentation skills at the final presentation will also be taken into consideration by us. So then in the remaining 15 minutes, I will briefly introduce the problems and challenges, some of them. Yeah, because we don't have the time to cover like all the research directions in memory systems. So I will just cover what is the most relevant to DRAM Bender and Remulator. So in general, the biggest problem we are facing today is that data access is becoming the major performance and energy bottleneck in modern computing systems. So most of our existing design principles, they cause great energy waste and also a great reduction in system performance. And the root cause for this is that most of the processing today is performed far away from the data it needs. Let's take a look at the conventional von Neumann computer architecture, where at a high level, the computer can be divided into three components: the computing unit, the communication unit, and the memory/storage unit. So yeah, we are focused on the memory system, so we just refer to this as memory. So in our current days, the computation part is, let's say, the processor. The communication is all the data links and buses. And for the memory and storage, the prevalent main memory technology is DRAM, and we use hard drives or solid-state drives for storage. So as you can see here, in our existing paradigm, we do almost every computation in the processor, so it's processor centric. But as you can see, because the memory unit is far away from the computing unit, this means like for every computation, there's like a lot of data movement involved. So this comes at great systems cost. And on the other hand, let's say our existing memory, let's call them dumb, because they almost have no data processing capabilities at all, and it acts largely as a passive device that takes instructions from the processor and just sends the data back and forth. So what are the consequences of this? So there's like this famous quote from 1996 that basically says like, the biggest problem in computing system is the memory. So if we quantize this problem, as you can see from this paper 20 years ago, that more than half, or let's say 55% of your execution time are spent on waiting for the data, basically. And this is from 2023, and it has not been improved a decade later. Let's say from this Google paper in 2015. So they analyzed the real workloads that are running in Google's huge data centers. They find that, again, for most of the workloads, more than half of the pipeline slots are spent on the back end. And among these back-end pipeline slots, more than half of the cycles are bounded by cache, or in other words, they're waiting for data to come to the processor. So this shows like why we care about memory systems in modern computer architecture. So I will give a brief introduction to DRAM. So here we have a processor, and inside the processor we have a memory controller. Each memory controller manages a memory channel where there can be multiple DRAM ranks on the channel. A DRAM rank consists of a group of DRAM chip that all operates in lockstep, and inside each chip we have a DRAM bank whose major components is a 2D array of DRAM cells. And inside each DRAM cell, we have a capacitor that stores data in the form of electric charge, and access transistor that connects the capacitor to the bit line so that the data can be transferred from the capacitor to the row buffer and be sent back to the memory processor through the bit line. And this access transistor is controlled by the word line. Basically, it controls whether the cell is connected to the bit line or not. And as you can see, like, because it's a 2D array, we can address the data stored in the DRAM by rows and columns. So the basic operation of DRAM is as follows. So first, the processor will send an activate command over the memory bus to the DRAM chip, and the target bank that this activate command is concerned will activate the DRAM row that the activate command specifies. And this activated and the cells in the activated DRAM row will transfer their stored data through the bit line and reach the sense amplifier. So after the activation process is finished, the data stored in the DRAM cells are now transferred to the sense amplifier. And like the working principle of the sense amplifier is like two coupled inverters connected head to back. It will like restore the charge level in the capacitor of the DRAM cell, and then the processor, the memory controller, can send a read command, which targets the currently opened DRAM row to select certain columns of data to be sent from the DRAM bank to the processor from the memory bus. And finally, let's say if you want to access another row in the same bank, because in most DRAM architectures, there's only one row of sense amplifier in a bank, which means you can only open one row at a time. you have to send a pre-charge command to basically close the open row and reset the sense amplifier, which prepares the DRAM bank for the next access. So the DRAM latency is long. So here we show like a lot of latencies. You will learn what these are concerned with in later meetings. But yeah, let's just take a look at this TRC latency. So this is basically the latency between two activation commands to the same bank, or in other words, like if you want to read multiple different data locations in the bank, you are mostly bounded by this latency, and it's like more than 50 nanoseconds. And although this is for DDR3, in DDR4, DDR5, like the value only gets worse, if not better. This latency only gets worse, if not remains the same, even in modern DRAM standards. And if you compare this to the operating frequency of modern processors, then you will realize, yeah, this is really slow. So in order to address like these problems, so there are like a lot of past papers that tries to modify the DRAM architecture so that we can either hide or reduce that long access latency. So I will just showcase some of the paper here. If you're interested, you can just like go and take a look of these papers. They may also provide you insights for your own project ideas. So we have SALP, which proposes to use the existing multiple sense amplifiers in different subarrays of the bank to increase the, let's say a sub-array level parison to hide the latency. We have tiered latency DRAM, TL DRAM, which puts an isolation transistor in the middle of the bit line in a bank to divide a subarray into a near segment where the access to that segment can be faster because of the shorter bit line, or a far segment, which comes naturally at the cost of a bit slower access latency, to offer the reduced latency at the near segment. We also have low-cost interlinked subarrays, which adds isolation transistors in DRAM in another way, such that we can enable two things. First, we can do very efficient bulk data movement at the granularity of an entire DRAM row, very fast within the same bank. And second, we can introduce heterogeneous architectures inside a bank, such that we can have a smaller but faster subarray that serves as a cache in the bank, and the previously mentioned fast bulk data movement can be leveraged to bring data in and out from that cache-like subarray. We also have CROW, which modifies the row decoder and command decoding architecture of DRAM chip, so that one activation command can open two rows in the same subarray. And because we are opening two rows, like there are more electric charge stored in two cells. So we have both increased performance and increased reliability. And if we dig deeper into the low-level DRAM architecture, we can have reconfigurable trade-off between DRAM capacity and access latency in DRAM by placing the access transistor in a way such that we can dynamically reconfigure how the DRAM cells, bit lines, and sense amplifiers are interconnected. And so besides those previous works that tries to modify the architecture of DRAM chip itself, we also have these following works that does not change the architecture of the commodity DRAM, but instead through extensive characterization, let's say using DRAM Bender, to harvest the operating margins in existing DRAM chips under certain operating conditions. Let's say for this adaptive latency DRAM paper, we find that in moderate operating conditions, let's say a room temperature and enough power supply, we can safely operate modern off-the-shelf DRAM modules with much reduced access timing parameters. And for this paper, DIVA DRAM, we observed that because since the DRAM array is because the DRAM cells are organized in a 2D array, so the cells that are farther away from the word line driver, farther away from the sense amplifier, the signals just have to take longer to propagate to those cells, and those cells are by design a bit slower than the other cells that are closer to the word line driver and or the sense amplifier. So by extensive characterization, we may also harvest more latency reductions from this inherent DRAM array characteristics. Yet again, like these kind of things can be characterized and analyzed by DRAM Bender. So the next important part in the memory system is the memory controller. The memory controller lies in between the processor and the actual memory device. So at a high level, this component resolves the contention to the memory bus and the memory device by scheduling memory requests from the processor in an efficient way. So one key question that one key responsibility of the memory controller is to how to schedule requests to maximize system performance. So the problem here is that as we enter the multi-core or even many-core area, there are many applications or many cores that shares the same DRAM controller. Let's say for those server class Intel Xeon processors, you can have like 48 cores, but you only have 6 or 8 memory controllers. So the goal is to maximize DRAMs. So for a single DRAM controller, its goal is to maximize the DRAM throughput, but this causes an issue for multi-core, or like where the DRAM controller is shared by many applications, so that this scheduling policy might be unfair to some of the applications. So most of the DRAM controllers, they apply the row hit first scheduling principle, or in other words, if there's a request that can be immediately served by the currently open row, it will be favored by the DRAM controller because this request can be served faster. So as a consequence, conventional DRAM controller will unfairly prioritize applications with high row buffer locality, or in other words, those applications that tends to access the same row in a short period of time. And the second common principle, that let's say there are no requests that will hit in an open row, then they will pick, let's say, the oldest request in the queue, and this, as a result, could unfairly prioritize memory-intensive applications because there are like a lot of requests from these applications that has a higher chance to become the oldest in the request buffer. So as a result, DRAM controller can be vulnerable to denial of service attacks. We can write simple programs to exploit the above two mentioned unfairness, such that the other applications that shares the same memory controller with our program will be slowed down a lot. So to solve those, we have many past proposals to improve the quality of service, QoS, of the memory scheduling policy, basically try to improve the fairness. And it's also very tricky to exactly define what is fairness in different contexts. That's also like a research direction, but at a higher level, there are many different ways to improve different kind of fairness in different situations. And yeah, I'm just like enumerating some of them here. If you're interested, you're welcome to study these papers in detail. Yeah, so I think we are a bit tight on time schedule, so I will just like quickly go through them. And of course, another more advanced research topic, because of the complexity in the DRAM scheduling decision and the potential very large system performance parameter space, we can try to use a machine learning approach to design memory controllers that can optimize itself according to different needs and different workloads. And second, besides performance, so recently we found significant reliability issues in DRAM as well, such that one can predictably induce errors in most modern DRAM chips. So this issue is called RowHammer. So at a high level, it's a very simple failure mechanism in modern DRAM that can cause widespread system security vulnerability, and it even get like very significant mainstream media coverage. So how this problem goes is that modern DRAM is prone to disturbance errors even if they passed the factory tests. Let's say we have a DRAM array here. We have the DRAM rows organized. We have the DRAM cells organized in rows. Let's say we open this red row. We open it, we close it, we open it, close it, open it, close it. We keep doing this. After a certain amount of time, we start to see bit flips or errors in the nearby unaccessed DRAM rows. So yeah, we call like this row that we access a lot, the hammered row, and the rows that have bit flips, the victim row. So basically, this issue is if you keep accessing a DRAM row enough times, it will accumulate enough disturbance in the nearby rows such that they have bit flips. And we have papers that shows that most of the DRAM chips you buy today, despite the DRAM manufacturers claiming that they are solving the problem, they are still vulnerable to this kind of redisturbance. So there are like a lot of papers that are from our group that tries to characterize and understand this issue. Notice that like almost all of these papers are using DRAM bender, and RowHammer related characterizations are like in general a very heavy use case of DRAM bender. So you should expect to see like a lot of project ideas that comes from this part. So here we have, let's say, the first paper that reviews to the academia and the general audience that RowHammer is a severe security vulnerability in DRAM. And notice that like this is in 2014, where the mainstream memory we test are DDR3. In 2020, our group also published this revisiting RowHammer paper, where we focused on more modern DRAM technologies, let's say DDR4, LPDDR4, and we find that although the DRAM technology has advanced many generations from 2014 to 2020, the RowHammer vulnerability only gets worse. And in 2021, we published a deeper look into RowHammer, basically studies how the RowHammer vulnerability behaves as we change a lot of external parameters. There's a temperature, access pattern, access timing, and we also study the distributions, the spatial distributions of these errors. We analyze and propose takeaways and challenges in order for future system designers to consider to build more secure DRAM-based memory systems. At the same time, we also tries to reverse engineer the existing RowHammer protection mechanisms that are already implemented in some modern DRAM memory chips, and we prove that these existing defenses from the manufacturer are not as secure as they claim. So this is also a very interesting paper that uses the DRAM retention error and DRAM refresh command to reverse engineer these in DRAM RowHammer protection in a very smart way. And this also involves heavy use of DRAM bender. So if you are interested in like this kind of reverse engineering stuff, yeah, these kind of like DRAM bender projects are also very good. So yeah, then I think we have reached the end of our meetings. So next, we hope we can have a short introduction of yourselves. So yeah.
So how soon? Before doing that, we need to end the live stream.